ABC is a right triangle at B, where AB equals 17 centimeters, BC equals 11 centimeters, and D is the midpoint of AC. Find the algebraic projection of AD in the direction of CB. Okay, in this example, we have this right triangle that looks something like this. We're told that the length of side AB is 17 centimeters. Here we'll leave off the units, while BC is 11 centimeters, and there's a point called point D, which is midway between A and C on the hypotenuse of the triangle. Our question wants us to solve for the algebraic projection of a vector AD in the direction of another vector CB. First, let's define AD. This is a vector that starts at point A and ends at point D, and likewise, CB is a vector that starts at point C and ends at point B. So the idea is we want to solve for the algebraic projection of this vector onto this one. To begin figuring this out, let's first solve for the components of these two vectors. Let's say that point B in our triangle is the origin of an xy coordinate frame. We see then that vector CB lies along the x-axis, and line segment AB lies along the y. From this perspective, we can define the coordinates of the 4 points A, B, C, and D. Point A has an x-coordinate of 0 and a y-coordinate of 17. Point B, because it exists at the origin, has coordinates 0, 0, while point C has coordinates 11, 0. But now, what about the coordinates of point D? Because point D cuts in half the line segment AC, that means its x and y coordinates are 1/2 of the side lengths of those two sides of our triangle. That is, the x-coordinate of D is 11 divided by 2, or 5.5, while the y-coordinate is 17 divided by 2, or 8.5. Knowing all this, we can now focus on solving for the components of our two vectors, AD and CB. Vector AD is equal to the coordinates of point D minus those of point A, all in vector form. When we substitute in for the coordinates of points D and A, we find that this subtraction gives us a result of 5.5 and negative 8.5. These then are the x and y components of vector AD. Next, let's calculate the components of CB. To do this, we'll subtract the coordinates of point C from those of point B, which means we'll subtract the point 11, 0 from the point 0, 0. This results in the vector negative 11, 0. Okay, great. So now we have our two vectors, and we want to solve for the algebraic projection of AD in the direction of CB. To solve for this, let's remember that the scalar, also known as the algebraic projection of one vector v1 onto another v2, is given by the dot product of these two vectors divided by the magnitude of the vector being projected onto. In our case then, what we want to calculate is AD.CB divided by the magnitude of CB. Substituting in for the components of these vectors, and recalling that the magnitude of a vector equals the square root of the sum of the squares of its components, we next start to compute our dot product by multiplying together the respective components of our vectors. Along with this, we notice that negative 11 squared is 121, and 0 squared is 0, which means that this projection equals 5.5 times negative 11 divided by the square root of 121. But then 121 is 11 squared, so that factors of 11 in numerator and denominator cancel out, and we're left with negative 5.5. This is the algebraic projection of AD in the direction of CB.